Yes, good morning, students. In the last class, we have discussed about energy bands in solids, and we have also discussed about energy band in intrinsic semiconductor. Yes, that was a basic regarding energy bands, and let us continue the same thing today. Yes, let me revise the concepts fast before going to move to the next concept. See here, yes, in the last class, our concept was energy bands in solids. Yes, based on the energy bands, the solids are classified into metals, insulators, and semiconductors. Okay, so based on the energy bands, the solids are classified as metals, insulators, and semiconductors. How? How they are classified means see how based on energy bands means whether that energy band, otherwise the energy gap between the, I should say the energy gap actually. So yes, the energy gap between the conduction and the valence band is large or whether it is less. Okay, or whether it is not at all there. That means if energy gap between the conduction and valence band is zero, then what happens? Yes, the thing is based upon the energy gaps between the valence and the conduction band, the solids are classified into three types, isn't it? Metals and insulators and semiconductors. How? Yes. See here, in solids usually there are two bands as I have said earlier. We are considering for valence band. Okay, so and along with that conduction band will be there, and we are just leaving the lower energy bands. Okay, so before valence band, it is not like that other energy bands are not present in solids. They are present, but the considerable changes will be taking place in the valence band, isn't it, as compared to the inner bands of the solid. So that's why we are considered with the valence band. Why? Because those are the band which are giving the electrons for the conduction. Here our prime importance is to study about the conduction. Okay, so in semiconductors we are studying for conductivity. So for that we need electrons from the valence band. So that's why we are focusing on valence band, and inner bands also there. Okay, and we are just considering valence band and the conduction band which exist after the valence band. Okay, so yes, see here, in between valence band and conduction band, if there is no any energy gap, what happens in metals? There will be no energy gap between these two bands. That means both the bands are overlapped. So look at this term. So these two bands will be overlapping on each other. So that's why the energy gap between them is zero. I can write over here the energy gap between the valence and the conduction band is zero. So such type of materials are called as metals. Okay. So here I can say here metals are, you can just give one more term to it as conductors. Okay. So all metals are conductors. So if you are calling conductors, then also it is right. If you are calling metals, means those are nothing but conductor itself. It's usually in conductors, the valence band and the conduction band will be overlapping so that there is no any energy gap. So energy gap is zero. That means the electrons in the valence band can easily move into the conduction band without any external energy. So no need of much energy, external energy needs to be supplied to the free electrons in the metal. Okay, so to conduct, that's why the in the conductors the energy gap is zero. Okay, so this is what the situation in conductors. If we move to the insulators, yes. So what will happen here? Exactly opposite to this situation will be here. That means in insulators, the valence band and the conduction band both are separated by a large energy gap that is greater than 3 electron volt. Look at this. Okay. So the energy gap between these two bands will be greater than 3 electron volt. Okay. So here it is large, as I have said yesterday, as it is large by because it is not about giving the external energy, it will be greater than 3 electron volt for one electron in the atom. It is not like that. Not for one valence electron. Here we are considering for solids. That means in semiconductors, as there are more number of atoms, more number of valence electrons. Yes, usually if I say a semiconductor or any solid over here, so atoms will be having more valence electrons. So for all those valence electrons, we have to supply the energy greater than 3 electron volt. See here, the energy should be greater than 3 electron volt. Okay. So that means we will be unable to give that much energy Why? Because here, yes, it is possible, but for not to all electrons. Okay, so all valence electrons should get that much energy greater than 3 electron volt. See, if I consider for diamond, it is the energy gap is about 7 electron volt. That means for one valence electron, if I am able to supply 7 electron volt, then it will jump to the conduction band and it will conduct. Okay, so here that's why it is not a less amount of energy, it is a very huge amount of energy. Instead of wasting that much of external energy, it is better to not to use insulators for conduction. Okay, so yes, coming to the semiconductors. Okay, so yes, before we do this, let me tell you one thing about insulators. Yes, what we consider as insulators. Yes, let me take wood, plastic. All these are called as insulators. If I supply this much the energy greater than the energy gap, then those electrons will take that much energy, but instead of exciting to the conduction band, they will get their ignition energy. That's why the wood will burn out. So that's why we are unable to conduct we are unable to see the conduction in insulators. Getting so coming to the next one, semiconductors. So yes, in semiconductors you can see the valence band and the conduction band are separated by energy gap which is less than 3 electron volt. Okay, so this much energy is not a big amount of energy. That means energy less than 3 electron volt. Yes, if I go for silicon, this energy gap can be for silicon it is 1.17 electron volt. And if I say for germanium, what is the energy gap for germanium means as both are semiconductors, that's why I'm taking example over here. It's 0.74 electron volt. You can see over here, these two are less than 3 electron volt. So this much energy, if this much energy we are able to give to the valence electrons, they can easily excite to the conduction band and conduct. Okay. So here, what happens means energy gap is very less than 3 electron volt. So that's why a small amount of excitation energy is enough to see the conduction in the semiconductor. Okay, so this is what happening with the semiconductor. So here, whenever the electrons jump from valence band to the conduction band, so when they jump from valence to conduction band, at that time they will be leaving behind holes in the valence band. So how many number of electrons are moving to the conduction band? That many number of holes will be created in the valence band, and those are also available. Those holes are also available for the conduction. So here in the semiconductor, both the electrons and the holes will conduct. Okay. So this is what the special case in the semiconductor. Okay. So this was about our last class, and now let us move to the next. Yes, we discussed about for in energy band in the intrinsic semiconductor also is coming to that. Look at this. Here again, I have given you the two bands. One is valence band, and next one is conduction band. So these black color lines are showing the energy levels in the bands. Okay. So here in these energy levels, yes, in the valence band there are electrons filled. Okay, so here, yes, if I consider the case at T is equals to 0 Kelvin, when the intrinsic semiconductor are at temperature less than or equals to, sorry, it is not possible for less than, it equals to 0 Kelvin, it is not possible for 0 Kelvin too. Okay, so it is the lowest temperature, so at T is equals to 0 Kelvin, what happens? All the electrons in the intrinsic semiconductor will be lying in the valence band itself, and they are not going to jump to the conduction band. Why? Because they will not be having enough thermal energy for jumping into the conduction band. Okay, so at T is equals to 0 Kelvin, at this temperature, the electrons will be lying in the valence band. There is no any electron in the conduction band, no any number of electrons in the conduction band means they are not conducting at 0 Kelvin. So that's why what I can say is intrinsic semiconductors at 0 Kelvin act like insulators, okay, like perfect insulators. Why? Because no electrons in conduction band, no conduction. Okay, so at 0 Kelvin. Getting? So now, if I move to the case where these semiconductors, intrinsic semiconductors, are available at a temperature greater than 0 Kelvin. That means if the temperature of the semiconductor is greater than 0 Kelvin, it depends what may happen. You see here, this is the different case. In the previous case, there was no enough thermal energy given to the electrons. Why? Because at 0 Kelvin, the electrons will not be having any extra thermal energy, okay, any thermal energy associated with them. So that's why, as I'm taking this case, at T is equals to 0, T is greater than 0 Kelvin, the electrons at that temperature, the electrons will be getting the enough thermal energy for jumping to the conduction band. So look at this. What may happen? These valence electrons, okay, when they are at temperature greater than 0 Kelvin, they will get the thermal energy which is needed for the electron to jump from valence to conduction band. So I can name it as excitation energy. Okay, so at that temperature, electrons will be getting excitation energy, and when they get excitation energy, they will jump to they will jump to the conduction band easily. So here, if I take these two electrons over here in the conduction band, the thing is they always try to occupy the lowest energy levels in the conduction band. Okay, so yes, these electrons will be jumping towards the conduction band, and what may happen? Yes, as they jump to the conduction band, they will be leaving behind holes in their place. Okay, so here I have taken two electrons in the conduction band. Okay, they have got excitation due to the thermal energy. So what is left in their place? They will be leaving holes in their place. Okay, so in the same manner, if I take these two over here, yes, if these two electrons are jumping here, means these two will be leaving two holes in the valence band. So yes, this is what happens at the temperature greater than 0 Kelvin in intrinsic semiconductors. Okay, so I can say at T is equals to 0 Kelvin, intrinsic semiconductors act like insulators, and at a temperature greater than 0 Kelvin, they act like conductors. Okay, so here now as I increase the temperature again, so as temperature goes on increases, the number of electrons excited to the conduction band will increase. Okay, so as they will be exciting more and more, there will be more and more conduction seen. So here one more thing you have to observe is how many electrons are jumping to the conduction band, that many holes will be created in the valence band. Okay, so this is what you have to know. So that's why I can say the number of electrons in the conduction band will be equivalent to the number of holes in the valence band. Okay, so this is about energy band. This is nothing but energy band, valence band and conduction band. Energy band in intrinsic semiconductor. Okay, so this is what here electron energy I have shown here. So this is electron energy, and as there is some valence to conduction, again energy will be increased. So that's why they will be jumping to conduction and they will be conducting. Yes, so again let me run it fast. At T equals to 0 Kelvin, intrinsic semiconductors behaves like insulator. Why? Because there will be no any availability of valence electrons. Okay, that means conduction electrons in the conduction band all will be lying in the valence band itself. Okay, so that is what during the case at temperature equals to 0 Kelvin. At a temperature is greater than 0 Kelvin, what happens? The electrons will be getting, yes, required thermal energy, required excitation energy. Okay, so that thermal energy itself acts as excitation energy. So those will be excited to the conduction band. So these electrons will be excited to the conduction band, and then if electrons are available in the conduction band, means what? They will conduct. Okay, so it is about the conduction and how many electrons are excited to the valence band, excited to the conduction band, that many holes will be created in the valence band. It means number of electrons in the conduction band equals to number of holes in the valence band. And the next thing is, as temperature increases, the conductivity of intrinsic semiconductor increases. It depends upon the temperature. Okay, so now moving to the next, that is for intrinsic semiconductors. Yes, look at that. What are the extrinsic semiconductors? We have done with intrinsic semiconductor. Moving to the extrinsic semiconductor now. What are extrinsic semiconductors? These are nothing but the semiconductors which are doped. Okay, so if to the pure semiconductors, if I am adding any impurity, okay, at that time what happens? Those will become impure semiconductors, or those may also called as doped semiconductors. Okay, to a semiconductor, yes, I can take silicon or germanium. For silicon or germanium, if I bring any impurity atom and add to it, at that time what happens? They are said to be doped semiconductors. And what is the need of doping? Why? Because in intrinsic semiconductors, the conductivity is less. But what we want is high conductivity, and that can be achieved by doping the semiconductors. This you all know. Okay. So yes, in extrinsic semiconductors, again we have to study about the energy bands. Yes, as extrinsic semiconductors are of two types. First one is N type and the next one is P type. For both the semiconductors, we have to study again the energy bands over here. And there is a difference between the energy bands of extrinsic semiconductors and intrinsic semiconductors. And you can see how it is. Listen. What are the type extrinsic semiconductors? These are the semiconductors doped with the elements of the fifth group of the periodic table, isn't it? So for a tetravalent silicon atom, what we will do? For that tetravalent silicon crystal, we will be adding a pentavalent atom. Okay, so by adding those impurities, the number of electrons in the semiconductors will be increased. So thereby the number of charge carriers will be increasing. So if charge carriers are increasing means what? The conductivity will increase. So this is what happening with the n-type semiconductors. And if I go for the energy bands in it, yes, as I said, here we are doping the semiconductors. So let me take. These are nothing but the silicon atom. Just a rough diagram for a silicon crystal. And now what I will do is, we will be replacing the atoms of silicon with the impurity atoms. So yes, this is what impurity atom. And yes, now look at this. What may happen when an unsuitable atom is placed in the single silicon crystal? Here it is going to change the energy bands, of course. See, before placing this in the crystal, what happens? All are nothing but the silicon atoms. Okay, so the energy bands will be there. So for regarding the silicon atoms itself. So if you are adding any extra impurity in the silicon atom, in the silicon crystal, what may happen? This extra impurity is going to change the energy bands in this silicon crystal. Why? Because see here, it is having different number of valence electrons as compared to the silicon atoms. So usually for getting the n-type semiconductors, we will be doping that semiconductors with the with the atoms of 5 valence electrons. Okay, so pentavalent atom is doped. Okay, so this is having 5 valence electrons, whereas all the silicon atoms will be having the 4 valence electrons. So number of valence electrons is different. The number of energy levels will be different. So energy bands will get altered, isn't it? So that's why in the energy band diagram, usually we were having a valence band and a conduction band due to the presence of extra atoms. It is not like that only it is doped with one impurity atom. There will be many impurity atoms added to the crystal, not with one atom. It is going to happen. Yes. So due to those number of impurity atoms present in the single silicon crystal, there will be change in the energy bands, and we can see some extra energy levels in the energy bands, and that extra energy level is nothing this one. So here you can see this green colored dashed line which is going to represent the extra energy level. These are nothing but the previous energy levels for valence and the conduction band. And here, due to the presence of impurity atoms, there will be extra energy levels created in the crystal. So here, what I am saying it is nothing but it is nothing but energy level of donor atom. So that means donor atoms means what? Here, as this pentavalent atom is added, it is going to share its four valence electrons to make a four covalent bonds with the neighboring silicon atoms, and there will be one extra valence electrons which is very less tightly bound to the what you call impurity atom. Okay, so that's why as it is giving an extra electron to the crystal, at that time I can say that it is nothing but a donor impurity. So the pentavalent impurity, when it is added to a tetravalent silicon crystal, at that time what happens? It will be giving free electrons. Okay, so each atom will give you the one free electron to the crystal. So that's why, as it is giving free electrons, those are called as donor impurities, and those donor impurities will be uh, giving you the extra energy level which is lying between the valence band and the conduction band. Okay, so now here how the connection will take place means, let me draw some electrons in the valence band. Yes, look at this. So this is about valence band electrons, and now see here I have shown you the donor energy level below the conduction band because this free electron, which is less tightly bound to the nucleus, will be having more energy, so that instead of lying over here, as it is also considered to be valence electron, but it is less tightly bound, so having high energy. So instead of drawing that energy level here, it will be at a distance from the valence band closer to the conduction band. That means it is having an energy level which is just slightly less than the conduction energy level. Okay, so that's why this energy level is placed below the conduction band, immediately below the conduction band. Okay, not above the valence band. Instead of here, it will be here. Why? Because it is having high energy. Okay, so the electrons lying in this energy level. Okay, the valence electron, this free electron is having higher energy as compared to these valence electrons which are tightly bound. Okay, as compared to this free electron. So now, what I want to do is, as this electron is less tightly bound to the nucleus, as this free electron, as this electron, extra electron is less tightly bound to the nucleus, if I give a very little amount of energy to this, means I can free this electron from the bond. Okay, so that's why it is lying in an energy level which is just lying below the conduction band. So that's why this needs just 0.01 electron volt of energy to jump into the conduction band. What I said is, as it is less tightly bound, less energy is needed to make it free. Okay, so that's why that energy will be equivalent to 0.01 electron volt. So if I give 0.01 electron volt, then the electron in this energy level will jump easily to the conduction band. Okay, so at that time what may happen is, as it will be jumping to the conduction band, there will be number of electrons, more number of electrons are available in the conduction band. So that's why in N-type semiconductors, what happens? Number of electrons available for the conduction is more as compared to the holes. Yes, these electrons will be jumping to this. How means if we are able to give enough thermal energy for this, then they will jump to the conduction band. So if they jump to the conduction band, what happens? there will be holes created in the valence band. So this is about energy bands in N-type semiconductors, valence band and conduction band. In between that, additional energy levels will be present due to the presence of impurity atoms. Okay, so that energy level in the N-type semiconductor is called as donor energy level. And here where these free electrons will be lying, and if I give this much amount of energy to diamonds, they will easily jump to the conduction band, and along with that, due to the thermal excitation, the valence band electrons also jump into the conduction band, and thereby creating more number of conduction electrons as compared to the holes in the valence band. So that's why in N-type semiconductors, electrons are the majority charge carriers. Okay, so this is about energy band in the N-type semiconductor. Yes, if I go to the P-type semiconductor, let's look at this. Here comes energy band for P-type semiconductor. It will be different from this. You can see. Just look at the green color line where that additional energy level is added in between the valence band and the conduction band. And yes, of course, P-type semiconductors are obtained due to the doping of a semiconductor with the trivalent, otherwise trivalence electrons. That means the atoms with three valence electrons will be added to the tetravalent semiconductor atoms. So during that process, what happens? Those uh, doping atoms, impurity atoms, will be creating holes in the crystal. As I have explained you in the p-type extrinsic semiconductors, how a doping of trivalent atom to the tetravalent semiconductor crystal will affect the crystal. Okay, that means those are going to give the more number of holes. Okay, here, so those holes will be accepting the electrons from the silicon bond. So here the thing is there will be silicon atoms in the crystal. So here, when it is doped with atoms of the third group, at that time what happens? There will be formation of three covalent bonds with mutual sharing of electrons, but one bond remains incomplete. Why? Because there is no any valence electron, fourth valence electron available in the impurity atom. So at that time what happens? Again there will be silicon bonds, isn't it? So what happens as there is a vacancy of electron over here, this trivalent impurity atom is creating a hole. So to complete this, what happens? An electron jumps from the neighboring silicon bond to the that impurity atom bond. At that time, here there will be creation of hole again. Okay, so thereby adding a trivalent impurity atom to the tetravalent semiconductor crystal will be giving out more number of holes. Okay. So now the thing is, the holes are having less energy as compared to the free electrons like this, as there was an electron donated by the pentavalent impurity. Okay, so this is having high energy as compared to the holes. So as holes are having less energy, they will be having their accepted energy levels immediately above the valence band, not near to the conduction band. Here, why these are near to the conduction band means the electrons are having high energy as compared to the holes. Okay, so that's why these are called as accepted impurity atoms. So those accepted impurity energy levels will be lying above the valence band, and look at the difference between these two. So now Here, if we are able to give an energy of 0.01 to 0.05 electron volts, at that time the valence electron can easily jump to the acceptor levels. So let me draw the valence electrons here. So here what happens? These valence electrons will be jumping to the acceptor level when there is an energy of 0.01 to 0.05 electron volt is given to the valence electrons. They will be jumping to the acceptor levels, and thereby when they jump to the acceptor levels, there will be creation of holes in the valence band. You can see like this. Yes, and again here also. So there will be creation of holes in the valence band. So thereby, if you increase the amount of excitation energy, at that time what happens? You can see some conduction electrons over here. That will jump valence electrons will be jumping to the conduction band. So the thing is, as compared to the electrons in the conduction band, the holes in the valence band will be more. So this is what happening with the p-type semiconductors. That means if I am able to give this much amount of energy to the valence electron, they will be jumping towards the acceptor level. Okay. So the thing is, next if you give further energy, they will be jumping towards the conduction band. The thing is, as these electrons will be jumping towards the acceptor level, at the time number of holes in the valence band will be increasing. Okay. So thereby these holes are also available. These holes are also counting for the conduction. And this is what happens with p-type semiconductors, extrinsic semiconductors. This is about energy bands in intrinsic semiconductor and extrinsic semiconductor. Just have a glance at it. Yes, here in n-type, the additional energy level will be lying below the conduction band, and here in p-type the additional energy level will be lying above the valence band. And now we will move to the difference between the intrinsic semiconductors and extrinsic semiconductors. Okay. Let's see here. As we need this band diagram for differentiation, so that's why let me keep these bands as it is. Yes. Coming to the intrinsic semiconductor and here extrinsic semiconductors. Yes. Let's look at this. Intrinsic semiconductors are nothing but the pure semiconductors, and extrinsic semiconductors are the doped semiconductors. So I can write first difference as these are pure semiconductors and extrinsic semiconductors are nothing but the impure, or these are doped semiconductors. Okay. And doped semiconductors means what? Again, they may be doped with the atoms of the elements from the group of periodic table, that may be fifth or third group. From the third or fifth group of the periodic table, those pentavalent or trivalent atoms are doped to the tetravalent silicon or germanium atoms. Okay. So here next thing is, in intrinsic semiconductor, the conductivity is low. Yes, I can write the electric the conductivity is high. The electrical conductivity is high. Okay. Yes. Look at this. Yes. In intrinsic semiconductors, there are no any allowed or permissible energy levels in between the valence and conduction band. Just now only we studied for energy levels in the semiconductors. You can see here in intrinsic semiconductor, there is no any extra additional energy level in between present in between the valence and conduction band. But see here, in the extrinsic semiconductors, you have additional energy levels. So that's why I can write here, there is no additional or allowed or permissible energy levels. No additional energy levels are present between conduction band and valence band. And here the third difference is, yes, there are additional energy levels present due to what? Due to what? Due to the presence of impurity atoms, isn't it? Due to the presence of acceptor and donor impurity, there will be additional energy level present between the valence and the conduction band. Coming to the next one, fourth one. Okay, so look at this. The conduction in the intrinsic semiconductors, okay, will be increasing with the increase in the temperature. I can write over here, as temperature increases, conductivity increases. But here, in extrinsic semiconductors, the conduction depends upon the concentration of doped atoms. Okay, it depends upon the concentration of doped atoms and also on temperature. Okay. Yes. So here in intrinsic semiconductor, one more. Let me take fifth difference. In intrinsic semiconductors, the charge carriers, that means the number of electrons in the conduction band and the number of holes in the valence band will be equal. But here in extrinsic semiconductors, in n-type semiconductors again, the charge carriers, majority charge carriers are electrons and the minority charge carriers are the holes. In p-type semiconductors, the majority charge carriers are holes and the minority charge carriers are electrons. So this is about the difference between the intrinsic and the extrinsic semiconductor. So now we have to study about the difference between the n-type semiconductor and p-type extrinsic semiconductor. Yes. The first thing is n-type semiconductors are obtained when a tetravalent semiconductor is doped with the for n-type semiconductor, when that semiconductor, intrinsic semiconductor, is doped with the pentavalent atom. Okay, at that time the n-type semiconductor is obtained and p-type semiconductor is obtained when it is doped with the impurity atoms from the third group. So trivalent impurity atoms will be there. So they will be resulting into p-type, and here the pentavalent atoms will be giving you the n-type extrinsic semiconductor. And one more thing is, next difference is, in n-type semiconductors, the number of electrons will be more, and the impurity atoms added to them are called as donor impurities, as they are giving more number of free electrons. But here in p-type semiconductors, the number of holes is more, so my majority charge carriers are holes. So that's why, as those holes will be accepting the number of electrons, so those impurity atoms added to them are called as acceptor impurity atoms. Okay. So next one is, if I go for energy band difference between n-type and p-type, you can see in the energy band diagram, in the n-type semiconductor, the additional energy level or the donor energy level is present just below the conduction band, whereas in p-type semiconductor, the additional energy level is the accepted additional energy level is present above the valence band. Okay, so this is what the main differences between the n type and p type semiconductors. Okay, I hope you all have come to know about energy bands in the semiconductors. So this is all about the energy bands and difference between intrinsic and extrinsic semiconductor, p type and n type extrinsic semiconductors based on energy bands too. So yes, let me finish the class here itself. Thank you.